This is Ideas Worth Exploring by Mark MacDonald. One of my favorite movies is an Australian comedy called Young Einstein. It's about an Australian boy named Albert Einstein, whose family farms apples and makes beer. But Einstein isn't interested in farming, his love is physics. So one day, after getting drunk, he comes up with the famous equation E=mc², and using that knowledge, he takes a hammer and a chisel and uses them to split an atom, and all the energy released from it adds bubbles to his beverage. It's a completely ridiculous movie, which is exactly why I love it. But what do the letters E, M, C, and squared have to do with splitting an atom? And why would you want to split an atom anyway? Other than making bubbly beer, of course. The short answer is nuclear energy. The long answer is what you're getting in today's episode. Let's start with a bit of history. On December 2nd, 1942, underneath a set of bleachers at the University of Chicago, Enrico Fermi split the atom. At least in a manner of speaking. What happened was that he led a team that built the first nuclear reactor, and inside the reactor, uranium atoms were splitting apart at a constant rate and releasing a steady supply of energy, the first ever man-made nuclear chain reaction. The first nuclear reactor gave off dangerous radiation that the researchers were not shielded from in any way. It was also so horribly inefficient that it wouldn't even have powered a light bulb. But they did it. They got energy from splitting the atom. This all took place in a squash court at the University of Chicago, where squash is a game that's similar to racquetball. The Russians had a spy giving information on the nuclear progress of the US back to Russia. But due to a translation error, the official report said that instead of a squash court, this all happened in a pumpkin patch. At the same time as all this was happening, a different nuclear reaction was taking place. 93 million miles away, hydrogen atoms at millions of degrees Fahrenheit were bumping into each other with enough force to fuse together and release energy, creating a different kind of nuclear chain reaction. I'm talking about the sun. The sun is a natural nuclear reactor, but of a completely different type than the one in the squash court. The sun doesn't split atoms, it fuses them together, and this also releases energy, which is weird, because fusing atoms together is the exact opposite of splitting them apart. Why can you sometimes split atoms and get energy out, and other times do the opposite and get energy out? I definitely had to look this one up. I'll get back to it after going over some background. As per usual, I'll start out with what the ancients thought about this topic. I do this because it gives a good place to start from. Some of the most intelligent people in history thought for a long time about a lot of things, and the only difference between us and them is our understanding of modern science. So the question for today would be, what did Aristotle think about nuclear physics? The obvious answer is nothing. He didn't think about nuclear physics at all because no one knew anything about it until Einstein and Fermi and all that gang came along. So maybe there's a better question to ask. According to Aristotle, why did the sun shine? Aristotle thought that the laws of nature were different on Earth than in the sky. On Earth, you can build a fire to give off light, but it's only temporary. Yet in the sky, the sun never stops giving off light. It never turns off. So he thought that maybe the sun was made of a perfect, unchanging substance that would never turn off. He called it ether, which is the Greek word that means glowing, and he thought that glowing ether would shine forever without ever getting used up. We now know that the sun will run out of fuel in about 5 billion years. We know this because we know what causes the sun to give off light. One of the great things about modern science is that we can now explain the laws of nature in a way that's the same everywhere. So whatever it is that makes the sun glow, we should be able to do it here on Earth. And as of the 1930s, we can. It's called nuclear fusion, but we're still not quite ready to go there yet. First, we're going to talk about atoms. The word atomic means having to do with atoms, specifically the part of an atom called the nucleus. The word nuclear means having to do with the nucleus. So while saying atomic something something or nuclear something something usually brings to mind danger and explosions, they should really be making you think of atoms, the small building blocks that make up everything. Never trust an atom, they make up everything. And yes, I'm aware that I've used that joke before, but I believe in recycling. After going over atoms, we're going to talk about two forms of nuclear power. Nuclear fission, which is when you split an atom to release energy, like in a nuclear power plant, and nuclear fusion, which is when you mash two atoms together to produce energy, which is what happens in the sun. And finally, we're going to talk about some of the history of the discovery of nuclear energy, which is a tale of spies and secrecy. And by the way, it's clearly pronounced nuclear, not nuclear. Nuclear. Is that clear? Okay, good. You should be used to talking about atoms by now. When you break up a leaf into little bits, you can break each of those little bits into little bits until one of them is atomos, which is Greek for indivisible, meaning it cannot be split any smaller. Except that's a lie, because nuclear energy is what you get when you split an atom. But all atoms are tiny. How does splitting an atom give enough energy to power a city? Well, first of all, you're not just splitting one atom. When an atom splits, we say it fissions. It breaks apart into multiple pieces, and under the right conditions, those pieces crash into the next atom over and cause it to break apart. And this can keep going in a chain reaction. Chain reaction just means a series of reactions where one atom reacting causes the next one, which causes the next one, like links in a chain. If the chain reaction gets out of control, you have a fission bomb. If you control how fast the chain reaction goes, you have a nuclear reactor. So you're splitting many, many atoms, but also each of those atoms is releasing a ridiculous amount of energy. We can blame Einstein for this. That is to say, we can thank Einstein for teaching us why this happens. I call it the Einstein diet. Atoms are fat, as in all atoms have mass. Einstein realized that this mass can be converted into energy. You've actually heard of this before. It goes like this: E equals mc squared. E, energy, equals m, mass, times c, the speed of light, squared. Why is c the speed of light? Speed in Latin is celeritas, which starts with a c. You see? So energy equals mass times the speed of light squared. It's possible to convert mass directly into energy. It's the ideal diet. You lose weight and get more energy at the same time. Except if you follow the Einstein diet, you have to become a nuclear reactor, which would probably kill you. But anyway, the mass is converted directly into energy, but you multiply it by this number c squared to do that. And that's a big number. Let me tell you just how big that number is. The speed of light is 300 million meters per second. If you square that, it's 90 quadrillion, or if you're British, 90,000 billion. By the way, a British billion is 1,000 times larger than an American billion. But no matter what language you speak, that's still a big number. A little bit of mass turns into a lot of energy. In fact, if you could somehow turn all the mass in a bottle of water into energy, then you would have 1,000 times more energy than a nuclear bomb. Oof. Yeah, remember what I said when I said you can convert mass into pure energy? Well, that's not quite true. You definitely can't do it. In modern times, only certain nuclear reactions do that, and they don't convert all the mass into energy, only a little bit of it. So you don't have to worry about your water bottle destroying a city. It would only destroy part of a city. The point of all that was that atoms are fat, and nuclear reactions turn that mass into energy. That's where the energy comes from. It's stored in the mass of the nucleus of an atom. Nuclear energy, energy stored in the nucleus. But wait, I haven't talked about the nucleus yet. Okay, a little background on atoms. I promise, we'll get to the spies and stuff soon enough. Because we're talking about atoms, I bet you can guess what's coming next. Yep, electrons, protons, and neutrons. You're going to become close friends with them by the end of the episode. Remember, electrons are the downers. They're always negative. Protons are the cheerful bubbles of sunshine. They're always positive. Neutrons are neutral. They neither smile nor frown at anything. Proton, positive. Electron, negative. Neutron, neutral. These are the three building blocks that make up an atom. An atom has two parts, a central region called the nucleus, surrounded by a cloud of electrons. The nucleus is where we get the term nuclear. Once again, nuclear just means it has to do with the nucleus, or the central region of an atom. The nucleus has all the protons and neutrons in it. And there's a circus-level balancing act going on there that you need to understand before we move forward. The balance is between two different forces that happen in the nucleus. First, electric forces. Remember that like charges repel and opposites attract. But protons are all positively charged, so that's a bunch of like charges all in one place. Why don't they fly apart? They do push against each other strongly, But this repulsive force has to fight against a different force. It's called the strong nuclear force. Protons and neutrons attract each other through the strong nuclear force. You can think of the neutrons like glue that's holding the protons together. Without enough glue, the positive charges of the protons would overcome the strong nuclear force, and the nucleus would break up. If there's too much glue, then weird quantum things happen that I'd rather not talk about right now, but it also keeps the atom from being stable. So there must exist a sweet spot with just the right amount of glue, or just the right ratio of neutrons to protons. And that's the reason that stable elements can't just have an arbitrary number of neutrons. They have to have just enough to glue the protons together. Now you have all the background you need for understanding the two types of nuclear reaction: nuclear fission and nuclear fusion. Fission is when a large atom breaks apart and releases energy. All the nuclear power plants on Earth use fission. Joke break. Why do nuclear power plants always sit next to aquariums? To put all the nuclear fish in. In contrast to fission, fusion is when small atoms fuse together and release energy. Fusion is what happens in stars that lets them give off so much light and heat. On Earth, we've made nuclear weapons that are capable of fusion. We've also made prototypes for fusion energy reactors. It's just that to start a fusion reaction going, you have to get the material so hot that it's hard to get out more energy than you put in. We can do fusion, we've just never been able to make more energy from it than we put in. Maybe it'll happen in the next 30 years or so. Except they've been telling us that fusion is only 30 years away for the last 100 years. But maybe this time it'll be true. I hope this explanation has cleared up some of your confusion. So, back to the question from the beginning of the episode. Why do some atoms fission and release energy, and other atoms fuse and release energy? The answer is a little ironic. All atoms, big or small, want to be iron. See? Ironic. Anything larger than iron can be split or fissioned to release energy. Anything smaller than iron can be fused to release energy. Why is iron so special? It's just that iron happens to be the point where different forces balance out. It goes back to the balancing act we talked about earlier between the two forces in the nucleus, where the electric repulsion between protons, positive charges and protons, has to balance against the attraction of the strong nuclear force that I likened to glue. When I explained that balance, I kept some information from you. I neglected to mention that these two forces are fundamentally different. The electric force can act at a long distance, kind of like how a magnet can repel another magnet even when they're inches apart. And yes, an inch is a very long distance when we're talking about atoms. But the strong nuclear force is like glue. It has to be really close to act. Once you get farther away than the diameter of a proton, the strong nuclear force is basically zero. So, here's the resolution to our fission versus fusion dilemma. A proton or neutron has only a limited number of other protons or neutrons it can stick to, because that's just how the geometry works. So the attractive gluing force stays the same even as the nucleus grows larger. However, since the repulsion between protons is long range, the repulsion grows as the nucleus gets larger, so that eventually it exceeds the attractive gluing force, and you can't grow the nucleus any further. That's why there aren't an infinite number of elements on the periodic table, because proton repulsion would break them apart. Effectively, this means that the attraction between the stuff in the nucleus is very large when the atom is small, and this makes the small atoms want to fuse. Then, once an atom gets too large and has too many protons, the repulsion starts to become more important, and the large atom wants to fission. The sweet spot that balances the gluing force and the proton repulsion is right around iron. Iron wants to neither fuse nor fission. It's happy just the way it is. That's not to say that everything in the world is going to burst into flames and suddenly become iron. It takes a lot of energy to start a nuclear reaction, so unless you can get really, really hot like the inside of the sun or the middle of a nuclear reactor, then you have nothing to worry about. Just two more things before we start talking about spies and bombs and stuff. The first one is Einstein. Remember that Einstein told us that E equals mc squared, meaning that mass can turn into energy? Well, that's exactly what's happening for both fission and fusion. It turns out that if you add up the masses of a bunch of protons and neutrons, you'll find that the number is larger than the mass of the same number of protons and neutrons when they're bound together in a nucleus. The whole is less than the sum of the parts. When they bind together into a nucleus, some of the mass turns into energy. That should seriously weird you out. It's not just a weird quantum thing. It's a weird quantum thing and a weird relativity thing put together. But it happens. Some of the mass turns into energy and is released. How much energy is released depends on how tightly the protons and neutrons are bound together, which depends on the two competing effects I just talked about. But that's the key idea of nuclear energy, that some of the mass of protons and neutrons in the nucleus gets turned into energy. The last thing is radiation. I have somehow managed to talk for all this time without explaining what radiation is. Well, I'm actually going to brush over the details, so I hope you'll forgive me for that. But what happens is that whenever nuclear reactions take place, stuff flies out at high speeds. The stuff flying out often fits into one of four categories. You can have a clump of 2 protons and 2 neutrons called an alpha particle. You can have a beta particle, which is usually just a high-speed electron. You can have a neutron flying out at high speed. Or you can have a gamma ray, which I'll talk about more in a second. Any of these will hurt you because when they hit into your molecules, they hit hard enough to strip electrons away. That's bad, but your body can heal. Except if they hit a piece of your DNA just right, they can break a piece of it off, and it can sometimes heal back with the pieces out of order. Your body can usually deal with this mutation, but sometimes it causes cancer. One final note. One of the types of radiation I just mentioned was gamma rays. Yes, gamma rays are what caused the Hulk to turn big and green. No, gamma rays will not cause you to turn big and green, but they might give you cancer. Gamma rays are the same type of thing as X-rays, just with higher energy. And X-rays are the same type of thing as microwaves, just with higher energy. And microwaves are the same type of thing as radio waves, just with higher energy. But that's a story for another day. Now we're done talking about the heavy science stuff, and I can get to the history of nuclear. As you're probably aware, the history is pretty explosive. In 1939, some of the physicists who discovered nuclear fusion, among them a man named Leo Szilard, became worried that someone would use it to make a bomb. They were especially worried about the Germans, who were governed by Nazis at the time and were seeming more and more like a threat. So Szilard wrote a letter to the president about it. But he doubted that the president would ever read it. So he went to his good friend Albert Einstein, and he had Einstein sign his name to the letter and pretend it was from him. But before they had a chance to give the letter to President Roosevelt, the Nazis invaded Poland and World War II started. So they waited for 2 months for things to die down a little so the president could give the letter his full attention. So President Roosevelt was presented a letter from the world-famous Albert Einstein saying that the Germans might be researching how to build a nuclear bomb. He quickly established a committee to consider the problem. And as committees are wont to do, the committee acted really slowly. But eventually, this led to the birth of the Manhattan Project, a fully funded project to create a nuclear weapon. Einstein later said that he regretted ever signing his name to the letter after he found out that it led to the creation of an atomic bomb that killed 100,000 people. But he also said that he felt justified at the time because of the threat that the Nazis would develop a bomb first. The American government was very worried that the Germans would beat them at making an atomic weapon. In 1944, a German scientist named Werner Heisenberg, one of the founding fathers of quantum mechanics, was delivering a lecture in Switzerland. The Americans sent an agent to listen in. He was given the instructions to shoot Heisenberg if it looked like the Germans were close to building an atomic bomb. The strange thing was, this wasn't just a normal agent, nor was he even a scientist. He was a retired Major League Baseball player named Moe Berg. Why send a retired baseball player? Because he was really good with languages. He was known as the brainiest guy in baseball because he was fluent in 7 different languages and had a passing knowledge of at least 12 others. And though he wasn't a scientist, he was very good at convincing people he was a scientist. Because of this, an American intelligence agency, the predecessor of the CIA, recruited him to be a spy. He spent some time spying on the Italians, trying to figure out if they knew anything about the German progress towards a nuclear weapon. They didn't know anything. So, when the lecture by Heisenberg happened, Moe Berg was the natural choice to go. He would prefer to shoot Heisenberg in private to make his escape, but if it was the only option, he would have shot him in the middle of the lecture hall and then taken a cyanide tablet to avoid getting captured. But as it happened, Heisenberg gave no indication that the Germans were anywhere close to creating a nuclear weapon, so Moe Berg was left without ever having to shoot his gun. Einstein never worked on the Manhattan Project, but almost every other famous physicist that was around at the time did. You've already met Enrico Fermi, who is the guy who built the first nuclear reactor in a squash court at the University of Chicago. There was also Glenn Seaborg, who discovered 10 new elements on the periodic table, including plutonium, which was used instead of uranium in one of the bombs. There were plenty of others, but I want to mention someone who would become one of the future rising stars of physics, and one of my favorite physicists of all time, Richard Feynman. Feynman was basically just a rookie. He had only earned his PhD a year before, but he was brilliant, and he definitely made life more interesting for the people around him. His part of the Manhattan Project took place at Los Alamos Labs in New Mexico. While there, he amused himself by picking the locks on his colleagues' desks. Many of the locks were combination locks that were left on factory settings, or used easily guessable combinations like birthdays or like the number pi. Sometimes he liked to prank his colleagues, and he once spooked his co-worker into thinking a spy had read through his confidential documents, though Feynman quickly owned up to it. When Feynman's co-worker Klaus Fuchs was asked who at Los Alamos was most likely to be a spy, he mentioned Feynman because of his safecracking. But as it turned out, Fuchs was actually the spy, and he had been sending nuclear secrets back to the Soviet Union the whole time. By one estimate, those secrets later allowed the Soviet Union to develop nuclear weapons a year faster than they otherwise would have. So, 3 nuclear fission bombs were created. One was tested in the deserts of New Mexico to see if it worked. It worked, and then they were deployed on Hiroshima and Nagasaki. World War II ended shortly after, but there was no return to the status quo. The Cold War became a thing. The Soviet Union made their first fission bomb. The US, not to be outdone, began work on hydrogen fusion bombs. Instead of splitting uranium, the energy from these bombs came from the fusion of hydrogen, and the new hydrogen bombs were designed to be 1,000 times more powerful than the previous fission bombs. And things only kept on escalating. There was even a proposal to drop a nuclear bomb on the moon, just to show that America had superior weaponry. Luckily, we did not nuke the moon. The Cold War ended, and no one has ever used nuclear weapons to kill people since the first 2 in Hiroshima and Nagasaki. In that time, we've also learned how to control nuclear energy to be productive. We can use nuclear fission, splitting uranium or a couple other kinds of fuel, to produce, and we do this to produce about 20% of the electricity in the US and about 10% of the electricity in the world. It could be more, but people are afraid of it, so proposals to build new reactors often get shot down, even when there's no good reason not to build them. In the future, we might be able to make fusion reactors that make energy from fusing hydrogen atoms. Fusion is probably safer and more sustainable than fission, but the technology isn't quite there yet because of the problems I mentioned earlier. Maybe it'll happen within your lifetime, or maybe not. Is nuclear energy dangerous? It's like a lion at a zoo. Lions are inherently dangerous, but at a zoo, they're contained so they don't hurt anyone. In fact, no one has died from a lion at a zoo since 2018. Yikes, bad example. Maybe tigers instead. A tiger at a zoo hasn't killed anyone since 2007. I guess the point is that you're probably more likely to die from an escaped zoo animal than from a nuclear accident, just because of all the precautions that are taken to make absolutely sure that a nuclear reactor is safe as safe can be. Don't be afraid of zoos either, though. While they're not as safe as a nuclear reactor, they're still generally pretty safe. Time for the summary. I would make a nuclear pun here, but I'm worried you wouldn't reactor well. In summary, nuclear reactions are reactions that happen in the nucleus of an atom. They come in two types, fission and fusion. Fission splits apart large atoms and turns some of the mass into energy, while fusion fuses together two small atoms and turns some of their mass into energy. The reason both release energy is because there's a balance between two forces, proton repulsion and the attraction of the strong nuclear force, which I liken to glue. When atoms are small, the strong nuclear force dominates and the atoms want to fuse. But when atoms are large, the proton repulsion dominates and the atoms want to fission. We can make use of these facts to make nuclear bombs or nuclear power. Richard Feynman is a hilarious man who liked to pick locks, but he wasn't a spy. There were spies, and they did their spying things, but the world is mostly safe now. Nuclear reactors have so many safety precautions in them that you're more likely to get killed by a tiger than by a nuclear accident. Nuclear power is still distrusted by many, but that's mostly because they don't understand it. I hope that after this, nuclear energy doesn't feel like a specter that could melt your face off, but instead like a bright hope for the future of energy. Thanks for listening. Next time we're going to talk about whether a tomato is a fruit or a vegetable. Peace. This has been Ideas Worth Exploring by Mark McDonald.